Yeah, so remember I said that now we're gonna be doing the integral test, right? So we're gonna be doing the integral test. I hope you did study this information. And according to it, I think only 2 people came to my inbox to inquire. I hope the others are fine. So now I said that we're gonna be doing the integral test. The integral test. So what happens from the integral test is that this test is being taken from the improper integral. So we are taking it from the improper integral. So yeah, I won't say, okay, let me do this. So what we do here, what we have, let's suppose, so I'm going to state this. We suppose that f of x is continuous, positive and decreasing function on the interval which is from k up until infinity, and f of n is equal to a of n. Then we'll have the following conditions. The first condition is if we have the integral from k to infinity of f of x dx is convergent so as this, you say, right? So this one is also convergent. And then the second condition, if we have the integral of f of x dx is divergent, if this integral is divergent, so is n equals to k of an. So if the integral converges, so the series will also converge. You see, right? So if it converges, then the series will also converge. Now we come to this. We say that, let's say we're given this. I'm given this question. Yes, I'm given this question. They say I should determine if the following series is convergent or divergent. All right, and the series is as follows: 1 over n then n. You see, right? Then they say we should first check if this converges or diverges. Now for us to prove this, first what we need to do, we need to let f of x, first you let f of x be equals to 1 over x ln x. You see, right? Then after having that, now what you need to do is state that it's this. You remember I said that from the theorem we said that this function, we suppose that f of x is a continuous, positive and decreasing function. So this function is continuous, positive and decreasing. So the second thing that we need to do is to state, right? We need to state that we can say since f of x is first is positive. So we see that f of x is positive, right? F of x is equal to 1 over x ln x. You see, right? And then now we realize that the denominator is bigger. You see, right? So since the denominator is bigger, the more this value approaches positive numbers, this function will be decreasing, to be becoming smaller and smaller and smaller. You see, right? So we can say that f of x is decreasing, is positive, and as x grows bigger, f of x let me say decreasing. We say, right? So we realize that this will decrease as this gets bigger, as x gets bigger, right? And for all x greater or equal to 2, f of x is continuous. So now remember here, let me write this in the form of integral so you can see. Remember, we have the integral there. It starts from 2 until infinity of 1 over, we let that be ln of x dx. So check this. For any value between 2 to infinity, this function will be continuous. You see, right? This function will be continuous. So it will continue growing big and big. You see, right? And then from here, we can have that this, it is equal to, now according to the improper integrals, right? If I take 2 and plug here, I don't get undefined. If I take 2 and plug here and then I get undefined, it means that I must replace that 2 there. But when I take 2 and plug, I don't get undefined, right? And when I take infinity and I plug, I get an undefined. So it means that I must replace this infinity. So I'm going to replace infinity by t. This will be the integral to t. 1 over x ln x dx. You see, right? And then from here I can decide, so anyone can decide, let's say I decide to use the substitution, or I don't even use the substitution at all. So I can integrate this. So let's use the substitution. If I let me let u be equals to ln x, then I derive this, get 1 over x dx. Then I realize that this will imply that x du is equal to dx. Then from here, we know we can have that this will be the limit as t approaches infinity of the integral from 2 to t 1 over x u x du. Then the x will cancel the x, we say, right? And then I say the limit as t approaches infinity, integral of 2 t 1 over u du. Then I integrate this. When I integrate that, I'll get ln. You see right now? I'll get ln of u to t. You see right? And then, since I'm dealing with a definite integral, don't forget I want to add those things of plus c. We no longer deal with those ones. So I have the limit as t approaches infinity. Since I didn't change these intervals when I was using the substitution, I must come back to plug my u. My u was ln of x. You see right? Then I come inside and now I plug this. This will be ln of ln t minus ln of ln 2. I put those brackets, right? And then, if I check, ln of infinity will give us infinite. So this will be infinite, right? The solution here will be infinite. So, now my conclusion is that the integral is divergent. You see right? Since the integral is divergent, and so the series is also divergent. This is the second property. The series is also divergent. We say right. So the series is also divergent. I'm sure we agree on this. Any question? So if there's no question, then we can start solving this. And then now we come to the second one. Now we're given, we have the second one, we have that they say we should check this, integral this from 0 ne minus n squared. Remember, first thing that you do, you let f of x be equals to x e to the minus x squared. You see right? That's the first thing that you do. Then you check. If we check this right, we realize that f of x is positive. We see right? Secondly, if now I start to substitute these values 0, if I substitute 0 there on x, if I substitute 0, I'll get 1. I'll get 0 if I substitute 0. If I substitute 1, I'll get something like this. If I substitute 1, e minus 1 squared, I'll get 1 over e. You see that this is positive, right? Then if I substitute 2, I'll get 2, 4. You see, this will always remain positive. So this will just go to the denominator, this e. So this will always remain positive. I'm sure we see this, right? So this will always remain positive. And if we plug more and more, this will be decreasing. If we plug more questions, more x values, this will be decreasing. Then f of x is decreasing function. Thirdly, I need to check if this is continuous. So if I plug from 0, right, I realize that there's no way I'll get undefined. If I plug from 0, as long as so I have to specify the the interval. You can say that f of x is the continuous you see, right? So this will be continuous. So it's continuous. So now after this, all these are met, I must come and specify the integral. We're moving from 0 to infinity of xe minus x squared dx. I'm sure you're shocked, why did I think of using u substitution here? So every time you come across such a complex integral, you think of u substitution first. So here's how you apply u substitution, right? Let's say I let u be you choose. Here I'm given two functions here, 1 over x times 1 over ln x. One function is easy to derive, one function is difficult to derive. I always let u be the difficult one to derive. You see, right? You always let u be the difficult one to derive. After letting u be the difficult one to derive, you now ask yourself, will this function, after I derived it, be able to cancel this x? You see, it did cancel out from here. You see, right? It did cancel out. So after it cancelled out, means that u substitution works. But if it didn't cancel out, I would go to by parts. You see, right? Then I come here again. Here I check if I can use u substitution. So between these two, between x and e to the minus x squared, which one is difficult to derive? It's x squared. You see, right? Then let's try to let that be u. So I'll let u be equals to x squared. Then I derive this, I get 2x dx. Then this would be du over 2x is equals to dx. Then I come back to substitute. This would be equal to the integral from 0 to infinity of x e to the minus u du over 2x. You see the x cancels out. You see, right? And then I take out the 1 over 2. So it means that u substitution works. Every time when it's e, don't let the whole e be u. You let its exponent, unless we are dealing with by parts. But if it's u substitution, every time you're dealing with e, you let its exponent be u. Then after deriving the exponent, you find that it can cancel the other thing. Then you realize that u substitution won't work. You see, right? So this is du. You remember how do we integrate u? How we integrate u, we do the opposite of derivative, right? Remember, for us to derive u, what we do is we keep e to the, for us to derive e to the u, we keep e to the u, and then we times by the derivative of the exponent, then times ln e, which is the base, right? And then if we are integrating, this would be the same thing, but it's like where I keep e to the u, then I divide. Instead of multiplying, I divide by the derivative of the exponent times ln base there on the denominator. So I'll come back to apply all these. I'll erase here, right, and apply improper integrals. I'm just trying to show you this first. So I would do this. You see, right? Then I have 1 over 2 e to the minus u over negative 1. You see, right? So this is how I would integrate that. Then this would become minus 1 over 2 e to the minus, I substitute back there, x squared 0 infinity. So this is how I would do it, right? But since we're dealing with this is all fine, but since we're dealing with these improper integrals, what I have to do first before I do all these integrations, first I need to look at my intervals. I direct substitute. Direct substitute 0, I don't get undefined. Not here. If I direct substitute 0, I don't get undefined. So let's go back and direct substitute. If I direct substitute 0, I don't get undefined. So it means that the first thing I would do is what? Change this to t. Because when I direct substitute e, I would get undefined. So this will be 0 t x e minus x squared. So now you won't be shocked when I use u substitution, right? To say, you ask yourself, why did I let u be equal to x squared? If I want, I can let it be minus that, but I want it to be x squared. And then this would be du is equal to 2x dx, and then this would be du over 2x, which is equal to dx. You see, right? And then I go back as I did. First I start with the integral, with the limit over t approaching infinity, 0 to t, then I have x e to the minus u du over 2x. Then we know that the x will cancel out. I take out the 1 over 2 of the limit as t approaches infinity of a minus u du. Then we know how to integrate that, right? Then we integrate it. It's a to the minus u over d over du minus u times ln a, which is the base. Then this will be 1 over 2 lim as t approaches infinity of a minus u over minus 1, 0 to the t. Then that would be minus 1 over 2 lim of t approaches infinity of a to the minus, plug back the u because I didn't change those intervals. Our u was x squared, right? 0 t. And then from here, I can just work out this. Then this would be, now I'm going to get a to the minus t squared, and then minus a to the minus 0 squared, and this would be minus 1 over 2 as t approaches infinity of a t squared 1 minus 1 over 2. You see, right? When I apply the limit here, this will become 0 minus 1 over 2. You see, right? Is it 0? No, this one is 1 now. E to the 0 is 1. I'd get this, and this would become what? 1 over 2. You see, right? So I'm sure you see that it's that simple for us to apply this. Any question on this?
Like, why did you say f of x is continuous?
Because if I plug in numbers from 0 up until infinity, I don't get undefined.
Okay.
So there's no question, right? So it means that I can say, therefore, the integral is convergent and So the series is also convergent. We say right, then that will be the case. Now, from the integral test, we can also look at the P series test. So this one, you should look at it and also know that we have a proof for it that can possibly come. So from this we have the P series test. So what the P series test says, right? It says that if we have k being greater than 0, then the summation of infinity n equals to k of 1 over np converges. You know that this will converge if p is greater than 1 and diverges if p is less or equals 1. So some have been asking me what if n starts from 2, from 3. Now the condition that we should use is when k is greater than 0. As long as k remains greater than 0, when it comes to a P series test, this should happen. You see, right? So now we'll look at some problems. Now we can see, let me so I think let me check. I think this proof is coming. Just that this proof is done on from improper integrals. So this proof is done from improper integrals, which we'll be doing tomorrow. So tomorrow we'll do the improper integrals. We'll also do the P series test. Now the idea is to know how to apply it. And then let's say now we're given, they come and say, let's say they say determine if the following series are convergent or divergent. Let's say right. And then we have A, so the summation of infinity n equals to 4, we have 1 over n to the 7. So now in this case we check, right? This is our k. So as long as this value here is greater than 0, you see, right? We're going to come and say here, you see here, p is equals to what? P is equals to 7, which is greater than 1. You see, right? So by P series test, the series converges. You see, right? As long as that is greater than 0. We come to B. Now we have this n from 1 over the root of n. So Now we realize that also this one, you see, right? This is greater than 0. So it means that we can check p-test. Here we know that this is the same thing as 1 over n to the 1 over 2. Now we realize here that p is equals to 1 over 2, which is less than what? Less than or equals to 1. And by p series test the series diverges. You see, right? So that's what we'll be checking when, just that we won't usually use p series test alone. It will be used within most tests. So that's what we'll be looking at in most times. So yeah, I think so far we'll come across questions that will require us to reduce. Yeah, we'll come across questions that will require us to reduce this. But for us to, before we can do that, we need to look at the comparison tests. Then we can come back to questions. So yeah, so for us to apply the integral test while we are reducing and applying the p-test series, we need to go to a comparison test. You see, right? Comparison test will be the one that will teach us about reducing. So it's much simpler when we are there at comparison test. Then what the comparison test says, it says that if we suppose that we have two series, you see, right? If we suppose that we have two series, this AN and BN, you see, with AN and BN greater than 0 or greater or equal to 0 for all n, and such that AN is less than or equal to BN for all n, then this will occur. Number 1, if we check the summation of B, this series, the second series which we got after reducing, we find that this series is convergent. We find that this series is convergent, then this one also converges. You see, right? Second one, if we find that this series A of n is divergent, then this one Bn diverges. So usually we can just look at this. So now let's check the questions that we're given here. So let me see, here I wanted to write, we always check Bn, right? So let me see Bn, then An also diverges. So now let's have questions, then we look at that. Now we come here, we have the first question, right? The first question says that it says that we should determine if the following series are convergent or divergent. You see, right? And then the first one is we're given the summation n from 1 up until infinity of n over n squared minus cos squared n. So the thing here is that when we are reducing, right, we should consider one being the bigger one being the smaller one. So remember I said that we say that from the conditions, we say that it's best if we focus on this condition only. We say that a of n should be smaller than bn. If this a of n is smaller than bn, then here's what will happen. Now first, we must know about this. We have constants. We have non-dominating terms, and we have dominating terms. So when we reduce, usually I focus on the denominator. You see right now, because the denominator doesn't add too much effect. When I reduce one of these, I must check, is it a constant? Is there a constant? If you know, so this one, this is like this, it goes like this. Actually, let me say, we go like this, right? We start here, we can reduce this one, or this one, or this one. Usually, we don't reduce this one, because it's the dominating one. So I compare between this. I said there's no constant, so I must compare between non-dominating terms and dominating terms. So I must check between n squared and cos squared n. Which one is dominating, which one is not? Meaning which one gives us bigger numbers, which one gives us small numbers. If I plug 1, I'll get 1 right here. Then if I plug 1 on cos squared that, I get 0 comma something. 0.2919 something. Then if I plug 2, I get 0 comma something. Still here I get 4. You see that here I get 2 if n is equals to 1, if n is equals to 2. You see right, here I'll get 0.1739 or 31, something like that. I realize that this one is a dominating term. It means that when I'm going to reduce this, you see right, I'm going to have this. I'm going to have n. I'm going to have n over n squared minus cos squared n. You see that this will be greater than n over n squared. I'll reduce the non-dominating, which is cos. You see that cos is the non-dominating one, so I'll reduce it. So if I'll have this, then this one we know that this will be equals 1 over n. Then this means that I can check this is my what? This is my, always you see that one said what said a of n should be, here it said that a of n should be smaller than bn. But the question is, what do you do when an become bigger than bn? So there's also from another book, they say this about comparison test, right? They say that if an, they say that if bn, summation of bn converges, usually we use this on a limit comparison test. If the summation of bn converges and an is less or equals to bn, then an is also convergent. You see right? Then they also say that if this bn diverges and now it becomes the opposite, an being bigger or greater than bn, then summation of an is also divergent. You see, right? So we can use this theory. You see, right? Now we realize that an is bigger than bn. And if I check bn, I find that it diverges, then I know that also an will diverge. You see, right? And I got here that an, this is what? bn. I got that this is like this. You see, right? So what will happen is I'm going to take the summation of n from 1 of this, which is bn, right? I said that this is divergent. I check if bn is divergent or convergent. This is divergent by harmonic series. We did harmonic series. Or by p-test. The p-series test is that this is p is equals to 1. You see, right? P here is 1, which is less or equals to 1. Hence, by p-series test, the series diverges. You see that harmonic series and p-test agree, right? Diverges. And so n over n squared minus cos squared n is also divergent.